Today I'm going to be looking at day three's notes, and day three notes takes those separable equations that we worked on in day two and we kind of apply them into word problems. So up here in the top box it says, in many applications the rate of change of the variable y. Now how we would see that would be dy dt, that would be the rate of change of y, is directly proportional to the value of y. So if something is directly proportional, we would say equals for is k, which is some constant, times y. That would indicate directly proportional. If it said, for whatever reason, that it was inversely proportional, it would look like this. dy dt equals k divided by y. That right there would be inversely proportional. Okay. Most of the things that we're going to see, though, are directly proportional, and that means that we just take the constant times y. So if we have this equation, dy dt, that's the rate of change of y, and it's directly proportional to y. And let's say that we wanted to solve that differential equation. Well, we did learn from day two that in order to solve this, we need to separate and integrate. So when I separate, I need this y to come to the left side. So to bring the y to the left side, it would become 1 over y dy. I'll go ahead and keep that k on the right side. It's just a constant, and bring the t dt to the right side. So now I've separated, and now I'm going to integrate. So now just take the antiderivative of each side. On the left side, the antiderivative of 1 over y dy is the ln absolute value of y. Over on the right side, the antiderivative of k with respect to t is kt. I'm going to put my plus c on this side. If I wanted to solve this for y, to make the ln go away, you learned in day two's notes that to make this go away, or we reviewed in day two, we make e the base. And whenever we make e the base of that natural log, they cancel each other off. And whenever this is up in the exponent, we can go ahead and write y equals. And then you learned a c-wrap, and that all of that is discussed in day two notes, that if you see a c up in the exponent like this, we can take it and wrap it around to the front, and my equation becomes y equals ce to the kt. That right there is the solution to this differential equation. This differential equation is a very popular one. It's when we have dy dt equals a constant times y. And why it's important, or why it's popular, and I have my calculator out because we're going to be using that in a little while. But why it's important or popular is because whenever we have an exponential growth or decay, we're going to use this y equals ce to the kt. What it will usually say is y is a differentiable function of t such that y is greater than 0, and y prime, which is dy dt, equals ky for some constant k. As soon as you see this, now sometimes you'll see it like this, dy dt equals ky. You don't have to go through the process of separating and integrating like we did here. As soon as you see dy dt equals some constant times y, you can jump immediately to this equation, because that is the solution. We proved it up here to this differential equation. Now in this solution, it's important to note that c is the initial value. So if the word problem ever says what the initial value is, we'll sub that in for c. And k is the proportionality constant. Something important to notice is that if it is growth, your k is greater than 0. And if it is decay, your k is going to be less than 0. So let's jump into a problem and see what this looks like. This was back from 1993, and it was about a puppy. And it says that a puppy weighs 2 pounds at birth. And so immediately when I see that, I'm going to come over here and write, at time is 0, the puppy weighed 2 pounds. And 3.5 pounds 2 months later. So 2 months later, time is 2, the puppy weighed 3.5 pounds. If the weight of the puppy during the first 6 months is increasing at a rate proportional to its weight, that right there, whenever it talks about that rate, that means that I'm allowed to use y equals CE to the KT. That's going to be the equation I'm going to use as I go through this. Then how much will the puppy weigh when it is 3 months old? So at time is 3, how much will this puppy weigh? So let's go into this equation and let's start plugging in things that we know. Y equals. C stands for that initial value. Remember, C was the initial value. Well, when time is 0, my initial value is 2. So I'm going to put a 2 in there. E to the KT. Now, the time and the Y are going to vary depending on which time we're talking about. We're trying to figure out when time is 3. But before I can just plug a 3 into here, I need to solve for K. If I know what my proportionality constant is, I can do this. So I'm going to use this piece of information right here to help me solve for K. I'm going to say at this certain time when Y is 3.5, I don't know what K is, but the time was 2. Let's use this equation and solve for K. So to do that, I'm going to divide both sides by 2. So I have 3.5 divided by 2 equals E to the 2K. How I'll get up there to that K is I'll take the natural log of both sides. So the natural log of 3.5 divided by 2. If I take the natural log of the right side, I just have 2K. And then if I divide both sides by 2, if I divide both sides by a 2, that looks like a 12, but I'll be able to figure out what my K is. So that's where my calculator is going to come into play. So into my calculator, back on the main screen, I'm going to type in the natural log of 3.5 divided by 2 over 2. That's my K value. Notice it's a big long decimal. I don't want to round it. I will go ahead and write it down rounded, but I want to store it. So I'm going to store it in my calculator. If you want to store it as the letter K, you can. A is usually a little bit easier to get to, but you can pick any letter that you want to. Let's see, the K is right here, so I'll store it as K. Green alpha, and then the open parenthesis. Oops. And then press enter, and any time that I need to grab that K, I'll just press K on my calculator. So on my paper, I'll go ahead and write down what K was. K was 0.279807894. I wrote down as much as I possibly could. Now, that wasn't the question. I didn't answer the question yet. The question asked, at time is 3, what is Y? So I'm going to go back to this right here. And I'm going to look and see what is Y. 2E K, which I'm going to put this in for K, times time is 3. So into my calculator, I'm going to do 2E K times 3. Remember, I had, can you see that okay? I had it stored as K. And if I press enter, I get 4.63. And if I look at my answer choices, answer choice B would be my closest answer at 4.6. So I might write down 4.630, but answer choice B is the answer to the question. Okay, let's flip our paper over, and we have 5 of these that we're going to go through. Problem number 2. Says, suppose that an experimental population of fruit flies increases according to the law of exponential growth. Immediately when I see that, I'm going to write down the Y equals CE to the KT. It's exponential growth. And it says there were 100 flies on the second day. So over here, I'm going to write when time equals 2. That's the second day. There were 100 flies. And there were 300 flies on the 4th day. So when time is 4, we had 300 flies. How many flies were in the original population? So the original population was at time is 0, and that's what we're looking for. So when I go into my equation, unfortunately, I can't plug anything in for C because I don't know. So because I don't know the initial condition, I'm actually going to have to use both of these conditions that I'm given. If if I use this first condition here, I have 100 equals CE to the K times 2. Now let's say that I also use this equation. I'm going to rewrite it down here. I would say 300 equals CE to the K times 4. And I'm going to use both of these. This is a system of equations. This is 2 equations, 2 variables. I'm going to use both of these to try to help me solve for C. We'll solve for C first. Okay, so to solve for C, let's take this equation, and if I were to divide both sides by e to the 4k, I'd have C. And if I take this equation and divide both sides by e to the 2k, I have C. Well, if this is C and if this is C, I could set those two things equal to each other because they should be equivalent to each other, and I should be able to solve for k. So I should say that 100 over e to the 2k should be equal to 300 over e to the 4k. That should be a true statement right there. So I'm going to go into my calculator, and to solve that, I'm going to go to y equals, and I'm going to graph both of these and just kind of see where they're equal. So 100 divided by e to the 2k, or 2x, and then in y2, I'm going to put in 300 divided by e to the 4x, or 4k. Then I'm going to hit graph. I want to check my window. My window is small, but it's fine. Well, I'm not sure if it's fine. We're going to take a look. There, oop, I do not see my equations. So let me go back to my window and let's bring them out a little bit. Let's just try and see what a standard window would look like. Also, let me freeze this. I'm going to go back and make one of these guys bold. I'm also noticing that I probably want a bigger window than I just put, because I'm just imagining that if x was 0 in this case, well, if x was 1 in this case, this would be kind of large. If I press graph right now, I might not see much. And so, oh, I take that back. There's my first one. There's my second one. I can see them both. And I want to see where they're equal. So even though I can't clearly see where they're intersecting, I'm going to press second trace, number 5, enter, 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 and the calculator will go over and find that intersection point. And the intersection point that we found is what k equals. So k equals 0.549. Again, I'm going to store this. So even though I'm in the graphing window, I'm going to hit second quit, store green alpha k. And so now that's stored. So now, if I were to go back to this equation that I have written right here, go ahead and do it over here. And I'm looking for y equals CE to the k, which I now know, and the time for this particular problem is 0. Okay. And so now if I just go in, I take that back. I'm going to rewind a second. I don't know what C is. I do know what K is, but I still need to figure out what C is. So before I can do this, let's figure out what C is. Let's go to right here, and let's say C is 300 divided by E to the 4K. Remember, we have K stored. And so my C value is all I needed, and so my C value is 33 1/3. Notice the question just asked what was the original population. So I could have used this, but this was easier. C equals 33 1/3, and the question said how many flies were there? Well, there can't be 1/3 of a fly, so I would say that there were 33 flies in the original population. Okay. Again, I could have used what I put up there, but I just, looking back at it, thought that this would be a little bit easier for us. All right, let's try number 3. Number 3 was way back from 1985. It was a BC question, but it is totally something that I think that we can do. And it says dy dt equals -2y. That right there looks like an exponential growth or decay. Right there, that's a differential equation. Dy dt equals kt. So immediately I can do this, CE to the KT, except for in this problem, I know what K is. My K is this thing. So I can say CE to the negative 2T. So I can jump right there without having to separate and integrate. I can go right there. Okay, so let's read the problem. It says, if y equals 1 when time equals 0. So we might want to write that down. It says time equals 0, y equals 1. What is the value for t, which y, so we're looking for t, when y equals 1/2? Well, at time is 0, that's really the initial condition. So I can really rewrite this equation as my initial condition was 1. That's what my equation looks like. And I'm looking for the time when y is 1/2. So all I need to do is go into this equation, and where I see y, put in 1/2. And we're going to solve that for t. So to solve that for t, I'm going to take the natural log of both sides. So the natural log of 1/2 equals negative 2t. And then it seems like it might be easy to solve. I just divide by 2, except when I look at my answers, none of them look like that. So I'm trying to see how in the world I could get to one of those answers. One thing you could do is just, if you were allowed to use your calculator, you could type this divided by negative 2 into your calculator and see which answer choice is equivalent to that. However, if we're not allowed to use our calculator, this is what I might do. Instead of saying the natural log of 1/2, let's come up here, I would write this as the natural log of 2 to the negative 1. Same thing as 1/2 equals negative 2t. Now, if you remember your log rules, to expand a log, if there's something up top, you can bring it out to the front. So negative 1 natural log of 2 equals negative 2t. And then if I divide both sides by negative 2, I get 1/2 natural log of 2 is equal to t. Well, that right there matches up with answer choice C. Okay, let's try number 4. Number 4 is in 1998. And it says, in 1998, the population Y grows according to this equation. Oh, again, this is my differential equation I'm talking about exponential growth here. So I can immediately go to Y equals CE to the KT. I don't need to separate and differentiate. That would waste my time. As soon as I see this, I can jump right here, where K is a constant and T is measured in years. If the population doubles every 10 years, find K. Well, if something doubles every 10 years, it doesn't matter what we start with. We're going to double it after 10 years. So the easiest thing to do when it says doubles, let's assume we just start with 1. If we start with 1, when we double it, we're left with 2. E to the K, and how long did it take to get from 1 to 2 or to double? Every 10 years it doubled. So this is my equation I'm going to use. I'm going to try to solve this for K. So I am going to take the natural log of both sides. The natural log of 2, that makes that E go away, equals 10K. And then I'm going to do the natural log of 2 divided by 10 is equal to K. Let's get the calculator in here. And into my calculator, I have the natural log of 2 divided by 10. And I get 0.069, which is answer choice A. Okay, last one. We're in 1993. These are old ones, but they are still very good problems. It says, during a certain epidemic, oh, that sounds familiar, the number of people that are infected at any time increases at a rate proportional to the number of people that are affected at that time. So we're talking about the rate proportional, and what this means is Y equals CE to the KT. Now we are given some initial conditions here, or some conditions I should say. If 1,000 people are infected when the epidemic began, so that was the initial condition, that needs to go in here for C. 1,000 people were infected at the very beginning. And then when it was discovered. Then it says 1,200 are infected 7 days later. So let's say at time is 7, there are 1,200 people infected. How many people are infected 12 days later? So how many people are infected 12 days later? This looks pretty similar to actually the first problem that we did. I do need to plug a 12 in for t, but more importantly, I need to solve for my constant k. So let's figure out how we can solve for our constant k. And to do that, we are going to use this condition. 1,200 equals 1,000 e to the k times 7. To solve this, I'm going to divide both sides by 1,000. And so if I divide 1,200 by 1,000, I get 1.2. Did I get those numbers? Yes. Okay. Equals e to the k times 7. And then I am going to take the natural log of both sides. The natural log of 1.2 equals 7 times k. I'm going to divide both sides by 7. So I'm going to have the natural log of 1.2, divided by 7. And that's my k value. I'm going to go ahead and store that as k so that I don't lose it. That's my k value. It was 0.026. So k is 0.026. So then the question was really asking, that just found me k. So now I'm going to go back to this equation. And y equals 1,000 e. K, I now know what k is. It's 0.026, which I'll just put k in the calculator when I type that in, times t. And I want to know how many people are infected after 12 days. So I'm putting 12 in for t. So into my calculator, I'm going to do 1,000 times e raised to the k, which remember we have stored, times 12. Oops. And I get 1366.908. And so if I had to choose the correct answer that would match up with that, I would choose answer choice C. All right, if you would like an extra practice problem on this, there is one whitebook problem that I've got listed, page 130, number 9. It is almost the same. This is almost the same as example number 1 that we did, as we did these 5 examples. So if you do try that one, you can refer back to example number 1. Okay, I hope that helped.